this video, we explore the implementation of an 8x8 Discrete Cosine Transform, DCT, in CUDA. The DCT, introduced by Ahmed et al. in 1974, is a Fourier-like transform that differs from the traditional Fourier transform by using only cosine functions as its basis. The DCT converts input data into the frequency domain, making it a powerful tool in engineering and scientific applications. One of its most notable uses is in MPEG video compression, where it plays a critical role in data reduction and signal analysis. This figure illustrates the operation of a two-dimensional discrete cosine transform, DCT, applied to an n times m block of pixels or samples. In the figure, Fij represents the original pixel values, while FUV denotes the transformed values in the frequency domain. The process is reversible, meaning the original Fij values can be fully recovered using an inverse DCT, IDCT. Apart from minor rounding errors, no information is lost during the transformation. This equation defines the two-dimensional discrete cosine transform, DCT, for an n times m block of pixels with values Fijs. FUV is equal to constants nu times mv times this double summation. Summing over I, j, that is, summing over all the samples of the m times n block. We have Fij times cosine 2j plus 1 times v times pi over 2m times cosine 2i plus 1 times u times pi over 2n. Nu and mv are constants given by this formula. Here k could be n or m. Kr equals square root of 1 over k if r equals 0, and equals square root of 2 over k if r is larger than 0. So if k is n, n0 is square root 1 over n, and other nu will be square root 2 over n. The corresponding inverse discrete cosine transform, IDCT, is described by the following equation. Fij is equal to sum over u and v for the block, with nu time mv FUV times cosine 2j plus 1 times v times pi over 2m times cosine 2i plus 1 times u times pi over 2n. In image processing, data are typically divided into macro blocks, where each macro block consists of an 8 times 8 region of samples. In this case, m equals n equals 8, and equation 3 becomes this. The separability of I and j is crucial. The Fij values can be organized into an 8 times 8 matrix. Also, for a given pair of u, v, the corresponding cosine values can also be arranged in an 8 times 8 matrix. The Cij value is given by this formula. It is equal to ni times cosine 2j plus 1 times I times pi divided by 2n. Ni is given by this formula. This square bracket term is the dot product of the rho v vector of f and the rho v vector of c, or rho v of f dot column v of the transpose of c. The left term sums over I. It is the dot product of column u vector of f and rho u vector of c, or rho u of c dot column u of f. So, in matrix form, we can express 10a as f equals c times c transpose. It turns out that C inverse is equal to C transpose. That means C times C transpose is equal to the identity matrix I. By multiplying C transpose on the left of both sides of this equation, we get identity matrix here, and by multiplying C on the right, we get identity matrix here. So we have C transpose times C equals F. Or F equals C transpose times F times C. Here's an example. Consider n equals m equals 4. The DCT transform matrix C is a 4 times 4 matrix. Using the fact that cosine pi minus theta equals minus cosine theta, cosine pi plus theta equals minus cosine theta, and cosine 2 pi plus theta equals cosine theta, we obtain this matrix. Now A, B, C are constants with equals 1/2, B equals square root 1/2 times cosine pi over 8, C equals square root 1/2 times cosine 3 pi over 8. Note that cosine 3 pi over 8 is equal to sine pi over 8. Thus b squared plus c squared is equal to 1/2. You can easily see that C times C transpose is the identity matrix. In the transpose, a row becomes a column. So the first element of the product matrix is a square plus a square plus a square plus a square equal to 4 a square, which is 1. The next element is this row times this row, which is a b plus a c minus ab minus a c and is equal to 0. And so on. Evaluating the cosines, we get this matrix. Sometimes DCT is referred to as forward DCT in order to distinguish it from inverse DCT, IDCT. The following shows a C++ implementation of the transforms. The cosine values are often calculated offline. Here is a simple program that calculates the C matrix values. Actually, in this program we evaluate the C transpose matrix. It is straightforward. It directly calculates the values using the formula in 10a.
This is a C program that generates the C matrix values here. Okay. Actually, it is the transpose of the C matrix, CT. Okay, so let's copy this. And we call this gen cosine .cpp. Okay, and paste this. Okay. So this is the program we need. Okay, so the n is 8. So the CT, the C transpose, is 8 by 8. Okay, and AN, okay, are the 8 constants. Okay, we define here. This constant A0 is square root 1 over n equals 8. Okay, other AK values are square root 2 over n. Okay, and so these are the A. And then the CT JV values, okay, is equal to AV times cosine 2j plus 1 times v times pi over 2n. Okay, so basically this term, right, cosine 2j plus 1 times v times pi over 2n, and we also multiply it by the AV constant. Okay, so AV constant is absorbed into the C IJs. Okay. And then we print out these matrix values. Okay, so now let's compile it. So we say G++ gen -O, and so when executed, so it will generate these matrix values 8 by 8. Okay, and we can use these values to implement, okay, and 8 times 8 DCT and IDCT program. Okay, this is a straightforward implementation. So we declared the two-dimensional C n times n by the values that we just generated. Okay, these values. So actually this is the C transpose, but for convenience we just call this C. Okay, and so this is the DCT function and IDCT function. So the strict implementation from this formula. Okay, we have copied this program already. So it is called DCT. Okay. So this is the function DCT, and so we have a double loop for U and for V. Okay, so it is to calculate all the values of the DCT, okay, region, okay, in frequency domain FUV. Okay, and so FUV is given by this formula. Okay, so you have this term times this term. Okay, 2j plus 1 v pi over 2n. Okay, so that's what we have. Okay, Fij times Ciu times Cjv. Okay, so it corresponds to say so this term. Okay, so this term and then times this term. The AV have been absorbed in the C coefficients. Okay, so and after this sum we get one FUV. So we do this for all the samples. I mean all the regions, all the pixels. And the IDCT, okay, again is straightforward. We basically use this formula, okay, to do the calculation. Okay, so this formula to do the IDCT. Okay, again it is straightforward. This is CJV. Okay, this is CIU. Okay, and then the annual MV have been absorbed in these C coefficients. Okay, and times FUV. Okay, so we get Fij, very straightforward. Okay. And we have a function called print elements to print out the samples. Usually the samples are in integer form. Okay, so we use sort, okay, to the array. N times n is 8. Okay, and our functions operate on doubles. So we have a function sort to double to change the integer values to double. Okay, so it is straightforward. We just use the double casting to cast an integer to a double. Okay, and also after the transformation, we need to change it back to sort. So basically we do a rounding. Okay, so a double per 0.5 and take the full function, then will give us the rounded value. So for example, if we have the value 7.1, okay, 7.1 times 0.5 is 7.6. Okay, the full function is 7. On the other hand, if we have a value 7.7, okay, 7.7 plus 0.5 is 1.2, 8.2. So the full function will be 8. Okay, so this is a rounding function. Okay, so this is the main. Okay, we try some integer values. Okay, Fij is I plus j, and then we declare the F double, okay, to for the functions. Okay, so sort to double to change this F integer values to doubles. Okay, and then perform DCT. Okay, and then change it back to integers, and then we print out the coefficients, the integer coefficients. Okay, and we perform the IDCT. Okay, and change the recover values to integers, and then print out the recovered IDCT values, and we can compare the two cases. Now let's compile this and see how it works. Okay, so we say G plus DCT minus O DCT. Okay, and then we execute this. So you can see that these were the original sample values. Okay, 0, 1, 2, 3, 4. okay, up to 14. And these are the coefficients of the transform. After transform, you get these values. And you can see that most of them are zeros. So that means the data here do not contain as much information as it appears, okay? Because many data values are correlated, okay? So in the finished domain, many are zeros. So it is much easier to compress the data in this form, okay? And here, these are the values we covered by inverse DCT, okay? So they are the same as the original values, as you can see here, okay? Now let's see how we do this in CUDA. We first consider using one thread. In this case, the CUDA kernel functions, okay, are quite similar to the functions implemented in C++. So we only need to change a two-dimensional array to say one-dimensional array. Okay. And also we need to pass in the cosine values. Okay. And because of this change, okay, so the Fij becomes Fi times n plus j and so on. Okay. Now let's copy this. Okay. Copy the DCT to DCT, when we call this one CU, okay, and we make the changes here. Okay. So all these are the same. This becomes DCT1 CU. One means one thread. Okay. And here we need to add the keywords global. Okay. Global, global. Okay. And we change this to the pointer to the array F, and this pointing to the array, basically one-dimensional array. And also we pass in the cosine values. Okay. And all these are the same. So here Fij becomes I times n plus j, okay, from this one-dimensional array. And Ciu becomes I times n plus u. And this is C times n plus 3. Okay, so these are the changes we need to make. Okay, and we can do the same thing for the IDCT. Okay, let's copy the code, okay, to way faster. So we just copy from here. So again, we just, instead of using the FUV, so this becomes U times n plus v and so on. Okay. So others are the same. We still have print elements, sort to double, double to sort. And the main need to be changed because we need to allocate memory for the device, for the GPU. Okay. So this is the code that we need. Okay. So we declare the variable df, dn, dc, and memory size that we need to allocate a size is n times size of double. Okay, so we allocate this, okay, memory for, so as 1D arrays. Okay. Now actually we could use CUDA Mellow Pit this function to create 2D array also, but this would be less convenient. It's more convenient to use 1D array. Okay, we just need to make minor changes here. Okay. And again, we transfer the data from the host memory to the device memory. Okay, the data. And then we use just one block, one thread. Okay, so dimension is 1, 1. Okay, and just one grid, of course. So we pass in this parameter grid dim, block dim. Okay, others are the same. And then this function CUDA device synchronize means to ensure that the data have been all processed before exiting the kernel. Okay. And then we copy the data back to the host memory. Okay. And then change it back to sort and print it out. Okay. And we do the same thing for the IDCT. Okay. At the end we free the memory. Okay. So we could copy this to replace our original main. So copy this. Okay, so we don't need this main anymore. Okay, we save this. Okay. So this is our new code. Okay. And now let's compile this. MVCC DCT1.cu -o DCT1. There's an error. 38. Okay, let's see. What's the problem? 38. Okay. Oh, okay. So we haven't changed this yet. Okay. So this will be times n plus v. Okay. So let's try again. Okay, so it compiles, and now we can execute this. Okay. So again, we got the same results. Okay, the original values, the coefficients, okay, DCT coefficients, and then the recovered values. Okay, and we can check the profile. Okay, so there's the IDCT and DCT time consumed. Okay, there's about 466 microseconds. This is 385. Okay, so about the same. And now let's see how we could do this using multi-threads. Okay, so we discussed before in previous videos that in the GPU, a grid contains one or more blocks, and a block contains one or more threads, as shown in this diagram. So this is a grid of blocks, okay, and we can have more than one blocks, and one block can have more than one threads. Okay, so a number of threads. Okay. So now in our implementation, we use one thread to calculate one sample. Okay, and we'll use one block, and this block contains 64 threads to calculate 64 samples in parallel. Okay, 8 times 8, okay, 64 samples. Okay, then each thread will take care of one UV. Okay, so one transformed values. Okay, one FUV. Okay, and so that means in our revised code, okay, we can get rid of the for loop. Okay, for v. Okay, that's been done by one thread. Now we have 64 threads to do this. Each thread will do one FUV. Okay. For the inverse, okay, then again to use one thread to calculate one inverse, okay, one IJ. Okay. And then when the main, we need to declare the block dimension to be n times m. N is 8. Okay. So now let's make the changes here. Yeah. Let's copy this to save some time. Okay. So we could copy this to dct.cu. Okay. And now we can get rid of this for loop, because we use 64 threads to do all this. Okay, so this for loop we can get rid of. Okay. And here we can get rid of the IJ for loops. Okay. And the IJ values, okay, would be the XY index of the thread. Okay, so this is IJ, one thread, one pair of IJ. Okay, okay, to calculate one Fij. Okay, and here we just change this to n, okay, n, okay. Others are the same. So now let's compile this. So this will be nvcc dct.cu, okay, minus o dct, and we could execute this. So again we get the same results. Okay, so we covered all the values. Okay, and now let's see how this works. DCT with multi-thread. Okay, now you can see that, okay, the DCT and IDCT, this only requires 8 microseconds as compared to the other case we have using one thread. Okay, so it requires that long to do it. Okay, so it is sped up significantly. Okay. So that's the multi-thread implementation, okay, of the DCT and IDCT, okay, in CUDA. Okay. So this is a simple, a straightforward 8x8 implementation of DCT and IDCT. Okay. Actually, there's a method that can speed up the process that's called fast DCT. In this method, we could break down the summation into stages, okay? And the number of calculations will be essentially n times not n, rather than n squared we have here. Okay, so even though we use one thread to do it, we still have this loop. Okay. We still have this double loop, okay, and this loop could be sped up, okay, using fast DCT, okay? And we'll discuss this in a later video, okay. So if you think that this video is helpful to you, please give it a like. Thank you for watching, and I will see you in the next video. Okay, bye.